तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
The previous lecture we considered one example that is consisting of say it is a problem related to n operand instructions, n is 0, 1 or 2, and then here is the 2 operand instruction format. Okay. Then we considered 4 bits for opcode, 4 bits for source data, that is one of the 2 data, and 4 bits for the destination data. Then while discussing these 4 bits, we said 2 to the power 4 16 combinations are possible, that is 2 to 16 opcodes are possible, and with this opcode field whether we are referring to no operand or single operand or double operand instructions must be identified. So, we said with 4 only 16 are possible, actually these are the 16 possible codes. Now, this is one way of coding, of course very economical in the sense all the 4 bits in that field they are used. So, starting from all zeros to all ones it goes, right, that is these are the only thing that are possible. Now, there is another way you can also create codes with n bits. Let us say with 4 bits itself. For instance, how about this? Suppose we have this is one code, then let us say this is another code, this is a third code, then we have this code, and then we have this code. Now, with 4 bits I can also create these 5 codes, right. Of course, it is nothing but a subset of this. Now, the point you have to notice here is if there is a 1 bit, there is only one bit in the entire field. Okay. Now, both these are possible. Now, if I say a code must contain 1, then 1, 2, 3, 4 possible combinations alone are there. Now, this is also one form of coding, right. But then when you do like this, being a subset, the entire 4 bits position, as in this particular case, they are not used. So, you can say that when you do the whole, when you make use of all the 4 bits and then fill in ones and zeros appropriately and exhaust all the possible combinations, then we get the entire thing 2 to the power 4. Otherwise, less than 2 to the power 4 also you can form a code. Actually, both these are in use. Now, a scheme such as this, when you have all the 4 bits, this would need a decoder, because just by looking at the code and by say looking at the position of ones and 0, you cannot make out what it is. You have to study all the 4 bits and the combinations. So, a decoder is needed in this particular case, whereas in this particular case no, it is not necessary. You can just see whether there is a 1. If there is a 1, you just by looking at where exactly the 1 is, you can make out. You do not need to study all the 4 as such. So, both these combinations are possible. For instance, a scheme such as this would be called a linear select scheme. Linear mainly because you have only one at a time in one of the different positions in a linear manner. So, we can form different types of codes. So, both these are actually in use. Now, what is the advantage of having this? The disadvantage we saw that you need a decoder later on to understand which code it is. Now, what is the advantage of this? The advantage of having this is you can include as many codes as this particular scheme permits, that is 16 codes are possible, right. Now, anything is going to be less, any other type of coding. Well, this is one point we have to note, mainly because we have to consider the second problem which will come to this. Now, let us take a look at the chart and then see what the second problem is about. The second problem says a CPU which addresses the data through its 6 registers in one of 12 different modes. Remember, I was talking about the instruction format in which we not only give the opcode, but also mode and then reference to register. So, we have to formulate that. Then this particular CPU is to be designed to support different types of instructions. The numbers are given that you have 10 arithmetic instruction, 15 logic instruction, 24 data moving instructions, 6 branch instructions and 5 control type instructions. In other words, the study of any instruction set will consist of studying each class of the instructions. Now, add, subtract for instance will form arithmetic instructions, then say OR, AND, NAND, NOR or exclusive OR, these things will form the logic instructions. Then data moving instruction, move from one register to another register, okay. Any transfer from memory location to register and so on so forth, these will form the data moving instructions. And 6 branch instructions, normally instruction by instruction this thing the program is executed, but then suppose you stop and then go not when you do not consider the next instruction, but then you take an instruction away, then you have to branch away and stop the normal sequencing operation. So, branch instructions are needed for that. Then 5 control type of instruction, there are different types of instructions here. For instance, if in a particular word a particular bit or a set of bits must be set, okay, they will be instructions. So, all these types of instructions will form an instruction set. Okay. Now, a CPU is to be designed to include as many, okay, we will come back to that. Now, of these instructions respectively, it says for arithmetic instruction 20%, then so on so forth. All these are either single operand or no operand instructions, that is it been grouped. The single operand and no operand instructions have been grouped here, and the remaining, the rest of them are double operand type. So, again we are back to the n operand case, there is no operand, 0 operand and 1 operand and then 2 operand case. Now, it says what is the minimum size of the CPU's instruction word. Now, we will note this point, minimum size, and then I will talk about it again later. Okay. Now, let us write down and then note down the various points. What did it say? Yes, maybe we can make use of this. Opcode, we have to find out the sizes in this particular case, okay. And we have to work out a few more things. This addresses data through its 6 registers. So, the source data will be referred to through 2 different fields. One half of the field will be referring to the register, okay, and another half of the field will be referring to the mode. So, mode of the source data, that is one thing, and similarly about this also. This is of course for double operand instruction. So, what it says is the CPU which addresses the data through its 6 registers, that is the number of registers you have in this particular one, 6, okay. Then 12 different modes, the number of modes 12, okay. Fine. Now, what is the question? Let us take a look at the problem again. It says, what is the minimum size of the CPU's instruction word? Now, working out the minimum size, the way you can do it is only by saying to accommodate reference to any of the 6 registers here for instance or for here, if you want the particular instruction word size to be minimum, the way to go about is only for decoding. Okay. In other words, we have to code, given that this will be a binary word, we will be using the binary thing, which means for referring to any one of 6 registers, you need 6 unique codes, okay, like this, and obviously this would mean you need at least 3 bits. Why? Because 2 to the power 3 is 8, and so you can accommodate certainly the 6 that you need. Okay. 2 to the power 3 is 8. This implies that you need a 3 bit code. So, now we have got that this register part, this particular register part of the field will be 3 bits in size. Agreed? The same argument with reference to modes. Modes, you have to accommodate as many as 12 different modes. 12 different modes, this implies that this minimum you need is 4 bits, because 2 to the power 4 is 2 to the power 4 is 16. Oh, the other way it must be 6 can be accommodated. Similarly, here 2 to the power 4 is 16, and so 12 can certainly be accommodated. You need 4 bits here. Okay. Now, the way we arrive at that is mainly because of we have to see, look at the chart, there is a minimum size. Okay. For instance, you need not go in for this. Now, for referring to 6 registers, you can also have the register subfield can also have 6 bits. Similarly, in the mode you can also have 12 bits, but then it becomes unwieldy. Okay? It becomes unwieldy. You are not fully utilizing all the things. Fine. Now, the question is how to determine this opcode size. That is the main problem, for which you have to work out the details. What are the details? Let us get to the chart. Look at the problem again. Well, we have these various class arithmetic instruction, logic, and so on and so forth, each of these, and of these how many percent are single operand and no operand is given. So, let us take prepare a table and then work out the details of that. So, okay, instruction type, okay, and the numbers of them. Then it has been given single operand or no operand. Okay. So, single operand or no operand, it is clubbed together. Then we have the double operand instruction. So, we have to work out. Now, first the arithmetic type of instructions, actually it does not matter what it is, arithmetic, logic, data moving, branch, control. Okay. Now, arithmetic type, it is given that the CPU must support 10 instructions, okay, and then logic type, the CPU must support 15 instructions. Okay. Then next is data moving instructions. Data moving instructions, we have 24. Then branch instructions, we have 6. Then you can also take a look at the chart, branch moving instructions, you have 6. Then control type instructions 5. Okay, have we included everything? 10 of arithmetic instructions, see the chart, 15 logic instructions, 24 data moving instructions, 6 branch instructions, and control type there are 5. Okay. Now, it is further given as read the chart again, it is given that 20% of this, okay, 20%, okay, oh I see, right, these are the numbers. Now say 20 already included here, type and numbers if you want to call it. Now 20% of this will be single operand or no operand. First let us write down, then 60% of this, then it says 50% of this, then 50% of this, then 60% of this. These are single or no operand, it says. So 20% of this, what is this? It will be 2, 20% is 1/5, right. So 2, then 60% of this, so that will be 9, then 50% is half, that is 12, again this also is 50%, that is 1, half of it is 3, then 60% of 5 will be 3. So how do you determine the double operand? Now why should we work out this other thing, double operand instruction? Because we have to see a common format, is it not? A common format is needed, and the common format will be for double operand case, right. That is the highest number of there is the instruction which refers to the highest number of operands. So if we work out for double operand, which we already have for some partial information we have here, that is source and destination, these are the two data, okay. These are the two data. Now this will give us some information. Now let us see about opcode we are working out. The except for the opcode part, rest of the information we already got for the double operand instruction, that is what it is. So if we know how many double operand instructions must be uniquely identified, then we have solved the problem, agreed, because that is what we are looking for. Now once you have the common format for double operand, later on it can be verified and then seen whether single operand and no operand cases can be accommodated with the same format. So fine. Now it is given that single, no operand case and double operand. So these are the only 3 combinations. So it is given that 2 of these are this single operand. So 10 minus 2, 8 of this will be double operand instructions. Similarly 15 minus 9, 6 of these will be double operand. 24 minus 12, that is 12, 6 minus 3, so 3 of these, 5 minus 3, so 2 of these. So the total number of double operand instructions will be 2 plus 3 5 plus 12 17 plus 6 23 plus 8 31. So there are 31 instructions, okay. So there are 31 instructions, double operand instructions, which must be uniquely identified. Now when that means we need 31 codes, we need 31 codes for double operand instructions alone, okay. What does it mean? Which means again going for the minimums, what is that? Take a look at the chart again, let us remind ourselves the minimum size has been asked of. So the same way the opcode also will have to be in this kind of a coding, okay. So the minimum would be 2 to the power 5, because 2 to the power 5 is 32, right, which accommodates the 31 that we need. That means we need at least a 5-bit opcode field. Now let us make sure that rest of them, the other things can be accommodated. Now 31 codes go for double operand instruction. So one code is left, is it not? 2 to the power 5 is 32. So one code is left. That one code will identify single or no operand cases, okay. You can just total them up and see what it is, and then check whether it can be accommodated, because of single operand, no operand. Single operand is one in which we need at least one data field, operand field, okay, for referring to the single operand. It means this particular field can be used as extension of the opcode, and this one has already 7 bits. So, with the remaining one code with 7 bit, 2 to the power 7 would be possible, right. So, maximum of 2 to the power 7, and remember there is only one code left. So, of that 2 to the power 7, 2 to the power 7 minus 1 will be used for maximum for single operand, because we need to have at least one for referring to the no operand of that, agreed, because there is only one code that is left, right. That one code only says whether it is single operand or no operand. Then we have 7, now 2 to the power 7 you can just work out and make sure that it is plenty, but remember that with 2 to the power 7 codes the entire thing cannot be used for single operand, right. Minimum is 2 to the power 7 minus 1 single operand, and then the remaining thing in that particular one will indicate no operand, because what is that, that is only one minimum, okay. Then since no operand is referred to, we will have another 2 to the power 7, okay. Anyway, we actually the problem itself does not say, we do not have information about how many single operand and how many no operands. As you can see that when you add up this, it is going to work out far less than 2 to the power 7, and that is for the combination of single and no operand. So, this is how you work it out. Now, what is it? So, it says 5 plus 4 9 plus 3 12 plus 4 16 plus 3 19 bit. This is the size of the instruction word. Take a look at the chart. So, minimum is this 19 bits, that particular thing is the instruction word. Good. Now, let us just quickly review the two things. The first problem we saw how given the number of rather given the size of the instruction word, how many instructions can be accommodated, how many different types of instruction. Now, in the second problem it is the other way, given the number of instructions and the type of instructions, what will be the size of it, right. Good. So, only variations of these will be there generally. Now, let us go on with the next problem, that is problem number 3, the next chart please. Now, this calls for information about, let us see the problem. You have to recall, okay, you have to recall whatever you had done early in the lecture. What is it? Just read the problem. The format of the micro word of a 30 state micro program controller. So, it is back to the controller design and micro programmed controller. So, micro program implementation. Now, this particular the format consists of 4-bit test field. You remember the format, generally we have test field, next state field and output field, that is what you have in any micro word for a micro program control. So, the size of it is given as 4-bit, 5 bits and 7 bits respectively. Now, given this information, what are your inferences about the number of inputs to the controller, then the number of outputs from the controller, then the algorithm for deciding the next state. Good. Let us see, let us quickly recall some of what we had seen earlier. It is just take an ASM chart. Okay. While discussing the ASM chart, what did we say? That from any given state, that is the present state, okay, some output may be generated, and then in that particular state I will just call state P, that is for present state, okay, whatever it may be. In this particular one, it checks for an input and depending on the condition of this particular input being true or false, two other states will be there, right. The system goes into either this true next state. So, I will call it true next state, and then this as the false next state. So, this is what it is. Now, in any state more than one input can also be checked correspondingly, and if you have more than one input, we can introduce some extra dummy states and finally bring it to this. For the one present state, there are only two possible next states. Okay, it is a very general thing, it can be done that way. Okay, let us not worry about that. Now, here what is given? Okay, now format of word we were talking about, right? That is what this problem states. The format is any microboard, if you take, I hope you recall that essentially you have this test field and then the next state field, next address or next state or whatever it is, and then you have the output field. Okay. Now, let us read the problem again. In this particular one, the controller is for controlling a machine which has a maximum of 30 states. Okay. So, the number of states will be 30, which means as per this particular diagram, okay, as per this 30 states, that means we do not know whether for a given particular state. Incidentally, what is this microboard is about? The microboard is for a particular state. So, for instance, this may be possibly a microboard for state P, okay. And then if it is for the state P, then it says what are the inputs to be tested. Now, this is nothing but this. The test field will have information about what are the inputs to be tested, and then depending on the particular input being true or false, the two next states, true or false next states, will have to be identified. Really speaking, there will be two parts. Okay. One thing which gives the true next address, the other thing which gives the false next address. So, there will be two subfields of this, and then the output that must be generated in that particular present state P, that is what it is. Okay. Now, according to this, right, if we have number of states as 30, then what do we need? How many bits do we need? How many bits do we need? Assuming as in the previous one, we go in the economic thing, coding, right. It is economic from the point of view of the number of bits usage, is it not? So, you need at least 5. So, because 2 to the power 5 is 32 and that will accommodate 30, which means the next, this particular one must be 5 and this part also must be 5. That is, we do not know for a given state, we have, that is in a given state we have to identify both the false and the true next states. So, you need a 5 bit subfield for say false next state and another 5 bit for true next state. Now, what has been given in the problem? Take a look. It says the test field is 4 bit, the next state field is only 5 bit, and then you have 7 bit output field. So, now we said we need at least 2 5s, but what has been given is next field is only 5 bits, test field is 4 bits, and then the output field is 7 bits. We have no choice, we do not have the 10 that we require, we have only 5. All right, now let us start. What is the first this thing? Let us see the chart. The number of inputs to the controller, which one indicates the number of inputs to the controller? The test field indicates, because in any microword you have to give information of for every state what are the inputs to be tested must be given in the test field. Okay. Now, it is given that the microword is 4 bit wide. Now, what do you infer from that? 4 bit means the number of tests can be so basically that is what we have to do. The number of tests, number of inputs, right, that is the same as test. So, test field indicates how many number of inputs can be there. When you have 4, what will be your inference? Go back to our coding. We have both linear select and we have decode type of arrangement. So, suppose we use this code. Suppose we use this code, the number of inputs will be only 4. If we use this code, it will be as many as 16, right. So, we cannot say what it is, all we can say is the number of inputs can be anything from 4 to 2 to the power 4, that is the only inference you can draw, 4 to 2 to the power 4, right. The same thing, let us finish off with the other one. What is the next one? The number of outputs from the controller, yes, similar to this, number of outputs. You would be tempted to say the same thing, what is the difference between this and that? Here also 7 to 2 to the power 7, right. Now, yes, we will accept the answer 7 to 2 to the power 7, okay. It is possible. It can be even less than 7, that does not matter, okay. We use one thing, maximum 7, that is what it indicates. Now, what suppose we say the number of outputs can be as many as 2 to the power 7. What is the implication of that? Think a little. Suppose the number of inputs should 2 to the power 4, right. Let us go back to the code. When we use this is when you have 2 to the power 4. What happens? At any time only one code is possible. Now, similarly, if you have the output 2 to the power 7 outputs, at any time only one output can be generated. Is it practical thing to do? Recall where we came across this microprogram controller and controller in general in generating the data path control signals for the data path, and in the data path in different parts, okay. We set the data path by enabling and disabling the different parts in the architecture, which means simultaneously different signals had to be generated. So, this is really meaningless, because if we have 2 to the power 7, then only one output can be generated at a time, okay. So, it is not really good, but anyway, maybe there is something in which it is possible, but in the normal, in the practical cases which you usually come across, it may not be very correct answer, okay. Well, theoretically 7 to 2 to the power 7 is correct, but practically speaking it will not be 2 to the power 7. Instead, what can happen is the 7 bit output, some part can be coded and some part may be separate. For instance, we may have say 1 2 okay 3 4 5 6 7 1 2 3 4 5 6 7, right. Now, this one has been 2 bit code, 2 bit code will be there. this will be a 3-bit code, these two will be separate, which means independently this or this, I will say this or this or this 3-bit denoted by C or this 2-bit denoted by D can be generated. This means actually simultaneously at least 4 signals can be generated, out of which these 2-bit together form one thing. So, this is neither linear select nor decoder, but it is in between these two, agreed. Now, it is the decode scheme within this C and D, and it is linear select or combinations of that also, A, B, C, D. Okay. So, you can generate them, good. So, that is about it. Now, let us come back to this third part of the question. It says, what is the algorithm for deciding the next state? I almost hinted what will be the algorithm. Now, the algorithm for the next state must indicate to you when the test fails, that is it is false, the input is false, then we have to indicate one 5-bit through a 5-bit code one next state. If it is true, through another 5-bit code the true next state. But it so happens that the problem states the only 5-bit is what you have. So, what is the way? That is, we cannot indicate both, that is what it means. So, for a given state P, let us say if it is P, it says test any one of these inputs, and then in that state P generate any one of the outputs as indicated, and it says you can give only one 5-bit next state. Now, which one? That means basically either you can give this true or this false, or we can give this false but not the true. Only one of this code is possible, agreed. One of these codes only is possible. So, obviously, that is the only way you can go about. So, what will be the what is the problem actually? It says what is the inference about the algorithm for deciding the next state. So, the algorithm must be somewhat like this. We can write the algorithm. If test is true, okay, if test is true, then next state will be, let us say, the present state plus 1, which you do not have to indicate anywhere. The present state plus 1, that is the next state. Otherwise, the next state is as given by the 5-bit field, okay. That is whatever is given in the 5-bit next field. So, if this is the algorithm, then it is enough if we give the which means basically in this particular one false. The false next state is being given, the true is not being given. Remember, it can be the other way, you can also put if the test is false, this, both are possible, right, good. So, if the test is true, the next state for the controller will be the present state plus 1, which can be designed in. Is it anything new? No. What do we do with program counter? Program counter, it is always incremented by 1, okay. Use the program counter to fetch an instruction, and then the next instruction is got from the next location, for which the program counter contents is incremented automatically. Only when it is not so, whenever there is a branch or a jump, okay, condition comes, then some other address will have to be loaded in. So, this same logic here too. If the test is true, okay, design, this has to be designed in. The next state will be automatically the present state P plus 1. So, as I have formed here, this one will, this code for T n will be p plus 1, that is the next one, whereas this false next state, this will be indicated to the 5 bit field. That is what this particular thing is. Agreed? Good. I hope you have noted enough points to see how exactly the format of a micro word is arrived at, and also important points such as assuming the next field as the present one plus 1, okay, that is an assumed next field, whereas this one will be the given next field which is given in the format itself. So, this we may say this particular one is assumed next field, assumed to be the present one plus 1, assumed next state address, whereas this particular one is given next state in the word itself, micro word. And another important thing is about when you can go for linear select and when you cannot really go in for. It will be meaningless to generate only one output at a time. Now, let us take another problem. This is to do with the instruction cycle. Let us see what it is. See the chart. Says for a given CPU, the first machine cycle M1 always consists of 4 states. Fine. You have to recall here instruction cycle consists of machine cycles which consists of states. So, here we have the details of that. Okay. The first machine cycle consists of 4 states, that is always so, and the remaining machine cycles consist either of 3 or 4 states. Okay. So, it may be 3 or 4 states, it depends on the instruction. Okay. Now, an instruction cycle consists of, now we talk about the instruction cycle which consists of machine cycle. It says a minimum of 2 and a maximum of 5 machine cycles. So, this particular thing is variable. Minimum of 2 would mean M1 and M2, let us say, and maximum of 5. So, M1 is always there, then M2, and then beyond that M3, M4, M5, let us say. Now, it says if the CPU's clock rate is 50 megahertz, why do we talk about clock rate here? Because this clock rate is the one which is going to define the state duration, right. Then calculate the shortest and the longest instruction execution time. How would you calculate? You have to look for an instruction which has minimum machine cycles and minimum states specifically, and the one with maximum machine cycles and maximum number of states. So, that will give. Now, there is an additional information here. What is that? If every memory access introduces one wait state, right. If every memory access introduces one wait state. Now, what is a memory access? How do you identify that? What is a machine cycle? A machine cycle is always entered into, right, whenever there is a bus activity. So, a memory access would mean actually accessing for some information over the bus. Now, let us work out some detail before you note down the data given in the problem. Okay. First of all, an instruction cycle, okay, will consist of, that is an instruction cycle that consists of machine cycles. So, it is given that this is a machine cycle. It is given that M1 of course is always there, and then it will vary. You may have in the rest of it, okay, for an instruction you will have only M2 minimum. Okay, we said it says that an instruction cycle consists of minimum of 2 machine cycles, M2. Then optionally you may also have M3, M4, M5, right. That is one thing. Another thing that is given is the yes, about the first machine cycle there is some information. What is it? It says that there are 4 states. Okay, about the first machine cycle there are 4 states. Essentially it means say 4 clock periods, let us say. Okay. Okay. What do you have? 1, 2, 3, or you must have one more. Okay. Do not worry about the non-uniformity of it. Okay. Now, there are 4 states. Now, this is fixed because it is given M1 always consists of 4 states, right, and the remaining machine cycles either they consist of 3 or 4 states. Okay. That is what it is given, each one of them, each of the remaining machine cycles, that is M2 to M5, they will consist either 3 or 4. Okay. And an instruction cycle consists of minimum of M1 and M2 and a maximum of M1 up to M5, that is given. Then of course, the CPU's clock rate is given, we will make use of it later, that is the clock frequency that is given is f clock is 50 megahertz, okay, from which we know that the state duration, so that is for each, say from this to this point. Okay. So, this particular one, that is if you put it as duration TCL 1 over 50 megahertz will work out to 20 nanoseconds. Okay. 20 nanoseconds. Good, we will check that later. Now, the shortest, there is one more point we saw. What was that? The last one. See the chart and the last line says every memory access introduces one wait state. Good. Every memory access, certainly, what is M1? Let us see, a machine cycle M1, it is fetching the instruction, there is a memory access there. Okay. For fetching the instruction, there must be a memory access. Similarly, M2, M3, M4, M5, they may be memory access or may not be, we do not know. Okay. Now, what it says is every machine, every memory access, which means corresponds to machine cycle, there is one wait state, means there is an extra state that is introduced, mainly because the memory is slow compared to the CPU. All right. So, now let us work out, let us note that there is one wait state for memory access, for every memory access. Now, this is this means essentially we have to consider this information whenever there is a machine cycle associated, which is usually associated with the memory access. All right. Now, the shortest what is that, execution time, right. All right. So, if you first what we will do is we will calculate number of states and then later on multiply that with the state duration. So, that will give us the execution time. So, for the shortest instruction, okay, how will you calculate? The shortest would obviously mean only 2 machine cycles M1 and M2, all right. There will be only M1 and M2. Now, during M1 we have 4 states, then obviously it is for fetching the instruction, which means a memory access. So, there must be one extra state. So, during M1 we should have 4 plus 1 5 states. Now, we are talking about shortest, okay, that is the first part of the question. Then we have M2. Now, M2 is another machine and it says it is either 3 or 4 states, okay, either 3 or 4 states. So, the minimum will be 3 you can take, and will there be a memory access? We do not know. There is no wrong, nothing wrong in assuming there may not be memory access, because you fetch an instruction here and then you, for executing that instruction you take 3, there may not be memory access. So, we can as well have it as 3 states only. Okay. So, this is for the shortest part, that is 5 plus 3 we have 8 states. this is the minimum. Okay. Then the longest one, the longest part of it, the longest instruction execution will be M1 as before, no change, there will be 5 states. Then we have M2 to M5, that is 1, 2, 3, 4 states, because the longest we have to include all the 4 states. So, there are 4 states, and again since it is longest, right, we will consider that each of those 4 machine cycles, each of them has 4 states, and we will, because it is longest, again we will assume that everything is a memory access, there is nothing wrong in assuming. Okay. So, 4 plus 1, 5 states, and then that is M2 to M5, right, we have 4 machine cycles into the number of states, how many? The longest is 4 and each has 1 extra state. So, we have 4 plus 1 5, 5 into 4 20. So, we have 25 states. Okay. So, for the first question, the shortest instruction execution time will be 8 into 20 nanoseconds, which is 160 nanosecond, and the longest one it is 25 into 20 nanoseconds, which is 500 nanoseconds. Okay. That is because that is the state duration. So, by calculating the number of states for a given instruction, right, you find that 8 is the minimum and 25 is the maximum, and every state needs 20 nanoseconds. So, this is how we arrive at it. Great.